Hi everyone, thanks for joining this video on the Technisci channel. I have a super exciting series to share with you, and that's beams. We are doing the graphical method for getting the reactions of beams, and we're also going to be looking at the analytical part so that we can check to ensure our answers are correct. So throughout this series, we're going to be learning about the different types of beams you can come across, the different types of loads that you can come across, and how to deal with all of that. So you really don't want to miss any aspect of this series. So come along with me for the journey. Make sure you watch to the end, and please let me know in the chat how the videos are for you. Let me know if you are learning, let me know if you are helpful. Keep the conversation going so that I can be in touch with you and know the impact I'm having on you. So this is part 1 of the series. We're doing simply supported beams, so let's get right into it. So let me just do a little on-screen demonstration. So here, you're seeing here, we have a diagram of a simply supported beam. Now, simply supported beams are those that have the supports at the ends of the beam. And so these are the type of beams that we'll be looking at in this one. And I want to also bring to your attention the type of load. Now, you have two main types of loads that you can come across in BMed, and that's the point load and the uniformly distributed load. So in this example, I'm showing you a point load applied. And in this example, you are seeing a uniformly distributed load. Now, it can be represented either in the way you're seeing it here, or it can be just the beam itself, the load of the beam itself, or any other way. But what will be key that you will recognize that it's a uniformly distributed load, we also call it a UDL. So what will let you know that it's a UDL, you will see the load per meter. So you're going to see, like, for example, 3kN/m. So that's basically saying this load is distributed, 3 kilonewtons of it is distributed for every meter of the distance that it spans. So what you would have to do is to ensure that when you are working with beams having a UDL, that you check the span, the distance over which it is being applied, so that you can know the full weight of the load. But we'll get right into that throughout this series. So make sure you don't miss a video. You never know what you're gonna miss. So let's get into our simply supported beam. All right, so here we have an example of a simply supported beam, and we know it is simply supported because you have the reactions at the ends of the beam. Now, the reactions is another name for support. The reaction term is coming from physics, where you know of Newton's third law of motion, which says to every action there's an equal and opposite reaction. So the action forces would be these forces that are applied, and then now these are reactions are the ones that are acting in opposition to keep the beam balanced. So usually you will see the beam having RL for the left reaction, RR for the reaction on the right. So just be mindful of that whenever you see the diagram. Now, I went ahead and I labeled the spaces between the forces. Now, this method is called Bose notation, and for that we use capital letters to label the spaces between forces or between loads, so that it's easier for us to work with it when we come to doing other aspects of the diagram. So that's a key thing that you have to do when you're doing these questions. In general, you would have gotten a question on paper, and then you'd need to draw up your beam. So that's what I did here. I put my beam in AutoCAD, and now I'm ready to go and work on getting the value of the reactions. So first thing I'm going to do, I'm going to be drawing what is called a load line. So the load line, as the name suggests, it represents the loads that are on the beam, and it represents it in magnitude to a suitable scale. Not so much direction, because the load line will represent the loads as well as the reactions, so we don't usually add arrows to our load line. What I must say about this topic in BMed that I love is that the name of the diagrams usually gives some hint as to what the diagram entails. So, for example, we're looking at our space diagram. Our space diagram is so called because we label the spaces. And so when you hear load line, it's called that because it represents the loads that are on the beam. Very nice, very simple to follow and to remember. So I went ahead and labeled the diagram space diagram and added the scale. The aspect of the space diagram that we scale is the spaces, basically the distance between each load. So I use a scale of 1 millimeter to 1 meter, which means that the distance between this load and this one would be 6 millimeters, and that would be equal to 6 meters. So that's the scale that I'm working with. So now I'm going to be drawing the load line. So I'm going to be using a scale of 1 millimeter to represent 5 kilonewtons. So note I'm using a single line to represent each load, makes it easier, but notice also they're all in one straight line. So what I'll do is when I'm done drawing these lines now, I'm going to be labeling so that we can identify each load. Just doing a quick dimension to ensure that I'm doing it correctly. I said I'm using a scale of 1 millimeter to represent 5 kilonewtons, so that is just about accurate to be 2. So after dimensioning, I'm just going to adjust the dimensions to the correct properties so that the size and all can be what I want it to be. So I'm going to do that and then we're going to continue. This is 2 millimeters representing 5 kilonewtons for each meter, so 5 2 is 10, representing this force here. Then we have 5 4 is 20, representing this one, and 5 6 is 30. So my distances are accurate. So now I'm going to be labeling. So from Bose notation, we note that this force, this load that's here, is between spaces A and B. And so it gets the name AB. And so when we bring it over to our load line, it will have that name. So this is force A. Then this second one, we would call it force BC because it's between spaces B and C. And then this force is between space C and D, so it is called CD. Getting the gist. So our load line represents the different loads that you have on the beam to an appropriate scale. That's basically what it is. And when you're doing your load line, you move in a clockwise direction for your loads. So AB, then BC, then CD. And you join them one to the other. So now I'm going to be labeling my diagram to show the scale that was used. Very important that we display our scale. And I hope line scaling is not difficult, but if it is, just send me a message in the chat and I'll be sure to explain it even further in my upcoming videos. But basically, you are saying every millimeter you draw represents 5 kilonewtons of a force. So, because AB is 10 kilonewtons, then it simply means that to represent 10 kilonewtons, I would have to draw 2 millimeters because 1 millimeter is 5. Then I need another millimeter to get 5 plus 5 to give me 10. And that's how we go about determining the length to draw based on the scale we have. So remember, just leave me a message in the chat to let me know if you are understanding how I go about scaling. So now I'm going to be putting in what we call a pole. Now your pole can be any random distance from your beam. However, many times we like to put it at a specific distance just to make it, a round value, make it easier to work with. So I'm going to use tracking. I'm putting it 40 out, but to scale, I'm going to put it to 8. 5 8 is 40. So that's where it ends up going. So now that I have the pole, I'm going to be labeling it. So the name of the pole, we usually give it the letter O. So now what we do, from each end of the load line, we will draw a line out to our pole. So now that we have our pole, our load line, and we have lines connecting each point on the load line to the pole, this diagram now takes on a new name. It's now entirely called a polar polygon. And like I said, the names for the different drawings in this aspect of BMed is really nice because it tells you or gives you an idea as to what is involved in that drawing. So this is now your polar polygon. All right, so now what we're going to do, I'm going to change my layer to hidden. So now I'm going to be drawing horizontal lines from each point on the load line, and I want it to go just beyond this reaction. So key thing, make sure ortho is on so that your lines are definitely straight. And then I can just copy. Now that we have these, we're going to be drawing now vertical lines from the point where each load acts along the beam. So whether it's the reaction or the action loads, whether they're going up or down, you draw a line from there. Awesome. So we're getting there. We're almost done. So now I'm going to be doing another diagram. So we have our space diagram, polar polygon. Now we're going to be doing our bending moment diagram. So for this one, follow me really keenly. From our polar polygon, we take line AO. Now AO is the line that is stretching from point A to the pole. So we take that line and we copy it using the base point as point A. And then on our space diagram, the space that is represented by A, which would be from this reaction to this load, we are going to put our line AO at the beginning of that space and make sure it falls below where we drew these horizontal lines. So I'm going to be trimming it off because we need to ensure that the line AO falls within the space of A, doesn't go beyond the space that is A. Then we're going to continue. Similarly, we're going to take BO, base point at B, and we're going to paste it at the end. Let me turn off ortho. We're going to paste it at the point where A ended. So continuing right there. And we trim it off again because we have to ensure that it is only filling the space for B. Now, please be very careful with this one. You have to ensure that it is only covering the space that it represents. So we're going for C now. Again, trim it off, making sure that it's only in the space C. So this space is C. And then finally, we're going to be doing D, which is this space. Then we trim it off. So there we have our polygon shaping up. And this is going to be called our link or funicular polygon. Again, link polygon. Good. And it also represents our bending moment diagram. So now what we do after we have copied these lines, what we do is to close the polygon. So we have A here, and this is space D, so we're going to close the polygon. Now observe for me. I'm going to make this into a different layer, but still keep the hidden line. Now observe for me. Now this member is spanning which space? We go back to our space diagram and see which space goes from one end of the beam to the other end of the beam. Now this is a simply supported beam, and so that is space E. Space E captures that span, but we don't have E on our diagram. Don't worry. What we do, we copy this line now, and this time we're copying it from this end, and we're going to paste it at the pole. And then we're going to trim it to where it passes our load line. And then I'm going to label. And that now is E, the closing side of the polygon. So I'm going to go ahead and label each member of this polygon and then get right back with you. Good, so we're seeing AO, BO, CO, DO, EO. And this now is our link or funicular polygon, otherwise known as our bending moment diagram. So we have done one drawing, and I can tell you that we already have the value for the reactions from a graphical standpoint. Let me show you now. So let's go back to our space diagram for a bit. So remember I said the spaces can be labeled using Bose notation in a clockwise direction, and the loads can be labeled using that concept as well. So remember this one was AB because it's between A and B, this one is BC, and so on and so forth. Now let's look at reaction RR. Yes, it has that name, but what would the name be if we were to name it based on Bose notation? Remember, we're going in the clockwise direction. So we see in the space, this is E, and then going clockwise, A. So this reaction by Bose notation is EA. So this is reaction EA. So let's now go over to our diagram and see if we're seeing EA. Awesome. That is the span for our reaction RL. And based on doing this diagram, it's so easy. All we have to do now is just to dimension that, and then we convert it according to scale and we get the value of our reaction. Simple as that. Now, from doing these questions, I find that it's easier or better to always keep your dimension to a precision of 1 decimal place. So now let's look at the reaction on the right. It is between space D and E, so it is DE. So let's go back to our load line and find that DE, and that's reaction right. Or the right reaction. Then I'm just going to match properties. And we see it's 8.2. So now we need to convert these according to the scale. Bearing in mind that our scale is 1 to 5, 1 millimeter of the drawing represents 5 kilonewtons. To determine how much kilonewtons 3.8 represents, what we'd have to do? Yes, simple. Multiply 3.8 millimeters by 5. So we get 3.8 times 5 gives us 19. Good. And then we have 8.2 times 5 to give us 41. Excellent. And don't worry, even if you use that different scale, like if you use 1 millimeter to 10 kilonewtons, trust me, you'll be getting the same answers, as long as you did it correctly. So we've now found the reactions using the graphical method, but we are not quite done with the diagrams we need to do. We're now going to be doing our shear force diagram, which is really easy. So for a shear force diagram, what we do, it's sometimes called a step diagram because it really does look like a step. So again, we are ensuring that we maintain our spaces. So let's look at our horizontal line here. It's coming from point A on the load line. So what we're going to do, we're going to be drawing our horizontal line from the beginning of space A to the end of space A. Very good. Now, when you get to this point, you realize, oh, there's a load here and it's going down. And it's AB, so it's going down to B. So we find B, and B is this second horizontal line, so we go there. Good. Let me just put on ortho to ensure. So then we carry this line now horizontally in the space of B. When we come to the end of B, we see another load, BC, this one right here, and it's going downward. So we're going to go downward. And then we go down to C, so that means we have to go across in the space C. Good. Then we come up on another load, CD, and it's going down. So we go down to D and then across. I'm going to stop right here for now, because now we need to go up. We're seeing this reaction here. We need to go up, but we don't know where E is in terms of a horizontal line. And I was specific not to put it in as yet, because sometimes the mistake is made when you're transitioning from BC, from B here, when you're transitioning from B here down to C. What will happen is when this E is put in, sometimes students make the mistake of stopping it here. So I try not to put in that closing side as yet. I try not to put in that E as yet until I have done all the other aspects of my shear force diagram. So I'm just going to copy this line now and just put it up to E. So I've really reduced my mistakes. So now I can continue. So from D, D is going up to E, and E is here. So we drop our line there. And then guess what? E goes all this way over to here, and then it goes up. And that is your shear force diagram. Now, from your shear force diagram, you can find the point where shear force is 0. Now, shear force is usually 0 on that horizontal line that covers the space between the reactions. That's usually where your 0 shear force is found. So I'm going to now be labeling the shear force diagram. So let me just go ahead now and show you what I've done that I've labeled. We label each horizontal aspect aligned with the load line. So we label it as it's aligned for the space. So this is A. Put A on both sides, just making sure that we did it correctly. This is B, it's in space B, it's along horizontal line B. This is E, it's along E, and for the space E, this is C, within space C and along horizontal line C. This is D, within space D and along horizontal line D. And that is awesome. So please also note that I put 0 at each point along that point where shear force would be 0. And now that we've done the graphical method, we can now, let me turn on my line weight a little bit so you can see it. I've turned on my line weight now so that you can see the beauty of your shear force diagram as well as your bending moment diagram, seeing your load line. So you're seeing the beauty of it now. And that is the graphical method completed. Completed graphical method to find the reactions of the beams. So now that we've done the graphical method, why not do the analytical method? Because we want to check, and it's good to know too, because sometimes questions may ask you for the analytical method. So it's good to know both methods. So I went ahead now and started the formula for the analytical method to find the reactions. Now, the formula for the moment is simply the force times the distance that it spans, and that's the distance from the joint or the hinge or the pivot, any of those. So once it's the distance of the force from the hinge, the pivot, then that's the distance you use. Now, a key thing that we normally use is we normally establish where we're taking moments from. And what that does is it gives us our point of reference. So for this first one, we're taking moments at the left reaction. And here's what happens when we do that. That's why it's so important. When we take moments at the reaction, the moment of that load, that reaction, now becomes 0. And let's say you had another force that was here, the moment of that would also be 0. And here's a simple answer why. No matter if this load is 1,000, if we are taking here and we're just assuming, we're assuming that this is where it's hinged at. If it's hinged there, 1,000 times the distance from the pivot or the hinge would be 0. And 1,000 times 0 is 0. So that is why wherever we take the moment as, wherever we're taking as the hinge or the pivot, any load applied there would have a moment of 0. So we're taking moment, and we usually take moment at one of the points where you have one of the unknowns. So our unknowns are the left reaction and the right reaction. So we take moment at one of those, and we also alternate at one of those reaction points so that we can eliminate that unknown and only have one in our equation. So now, taking moments at RL, we analyze all the loads that are acting. And guess what? These loads that are acting, if we hinge it here, can cause the beam to do what? To turn clockwise or anti-clockwise. So if we hinge this beam here, which direction will force AB turn the beam? We look at it from a clockwise or anti-clockwise perspective. And so I went ahead and grouped each member. So I'm going to rotate now. So if we consider the beam only has one support now, and that's RL, and then we apply the 10 kilonewtons at force AB, how is the beam going to turn? It's going to turn clockwise. Awesome. So that would be a clockwise moment. Moving over to BC, if we apply the force at BC, it's going down. How is the beam turning? Also clockwise. Going out to CD, if we hinge it at the left reaction and apply CD, which direction is it going? Also clockwise. So with the hinge at the left reaction, we have 1, 2, 3 forces that would be turning the beam clockwise. Now let's look at the right reaction. The force that is applied at the right reaction, pushing up, which direction is it turning the beam? It's turning it anti-clockwise. So we have one load that's turning anti-clockwise and 3 that's turning clockwise. So now let's go over to our formula. So you would be familiar. So you may be familiar with these symbols from math, and it simply is a sigma and it stands for sum. So taking moments at the left reaction, we're applying now the law of moment, and it says that the sum of the clockwise moment, Cm, is equal to the sum of the anti-clockwise moment, and that's for a beam that is in equilibrium, which is a condition of this beam that we're working with. It is in equilibrium, and that's why we can go ahead and calculate the reactions. So it's in equilibrium, so the sum of the clockwise moment is equal to sum of the anti-clockwise moment. Good. So when we hinged it at the left reaction, we said 1, 2, 3, we're turning it clockwise. So now let's go. That's 10 kilonewtons by 6 meters. So I'm just going to put 10 times 6, and it says sum, so we're adding the moments, and moment is force times distance, so we're adding those. The next one now, BC was 20, and it's the distance of 20 from here, so it's not 7, but it's 7 plus 6, which is 13. So it's 20 times 13. Says sum, gotta add the others. So CD is now 30 times 5 plus 7, 12, plus 6, 18. So it's 30 times 18. And those are all the forces that were turning the beam clockwise. So now we're going to look at what was turning it anti-clockwise. And it was the right reaction. So we just use right reaction times what's the distance from this pivot. It's 3 plus 5, 8 plus 7, 15 plus 6, 21. So now we have to do these calculations. So now we know that 10 times 6 is 60. So I'm just going to do all the calculations so we can see it in the window here. So now we just divide. So RR is equal to 860 divided by 21. And if you want to catch how I did this transposition, there's a video on my channel about transposition, and I'm going to put the link in the iCards and in the description below. Check it out. And AutoCAD does that automatically, really cool. So that's equal to 40.95, so that rounds to 41 kilonewtons. That's the right reaction. Let's see if it's matching up with what we have so far. Right reaction, 41. Yay, excellent, very good. So now let's look at the left reaction by applying the same concept. So applying the same concept, if we hinge this beam at the reaction on the right, and then we apply this force, the beam would turn anti-clockwise. This one would also turn it anti-clockwise, and this one would turn it anti-clockwise. The reaction on the left, however, would turn it in a clockwise direction. So when we take moment at the reaction on the right, we have 1, 2, 3 that will turn the beam in an anti-clockwise direction and 1 that will turn it in a clockwise direction. So let me now set that out and do the calculations. And there you have it. So the left reaction from our calculation was 19, and that's what we got when we did the graphical method. So that is correct. Excellent. Congratulations. So how was that? I hope you got it. I hope you were able to follow along with me. Now, if you were just watching and you say, no, let me just see what you're doing first, make sure you go rewatch and do the procedure so that you can master, because we're all about acing or BMed exams. So catch me in part 2 when we do will I do an overhang beam or a cantilever beam? Who knows? Catch me in the next one to find out. Thanks for joining.